Okay, this is the video tutorial for homework number 2, and it's associated with lab 52. Okay, so there are two problems here, and you're asked to submit only the results for problem 1. Okay, the second problem is right there, and I have reversed the order of this so that the submission in the morning lab is different. Okay, so let me solve this problem first, and then we're going to go and worry about the second one. Okay, so let's see. We have an object like that, and the top of this is pinned somehow, and the bottom of it is pulled down by a given amount. You're asked to model this problem, and then with the most appropriate element, take any planes of symmetry into consideration that applies, and then find the force that is needed to cause that deformation. The first thing you have to realize is that it is not the most appropriate element for this problem is beam element. Do not make an object like that and then measure it with those solid elements, okay? That's what most appropriate element means here. Do not kill a fly with a cannon, okay? Now, the second thing is that there's two ways to proceed. You know that you have to model half of this. If that is the case, you have two choices. You can draw half of this as a sketch, join it, and then proceed, or you can draw a half a circle in space, which is a wireframe, and then uh, proceed. Okay. Uh, yeah, join it, and proceed. I don't think you need joining there, but we're going to find out. So look, for the morning class, morning lab, where this is not the problem to be submitted. Okay, I did this problem with drawing this thing as a sketch and joined it. Okay, uh, I, I will do the same thing here, but I'm telling you that if you draw this thing as a wireframe, half a circle in space as a wireframe, I don't think you need to join it. Okay, so I'll leave it to you to experiment with it if you want. Okay, but if you do it as a sketch, you have no choice. You got to join it. So let's go ahead here and start a part file. File, new part. We will run into some issues here, generally speaking, for this problem, and I repeat exactly the same steps, same mistakes that I made with the first lab, because you get to learn something from it. Okay, on a convenient plane, on that vertical plane, you sketch half a circle. Do it any way you can. This is how I'm going to do that. Okay, I use this icon for circle. Dimension it. This radius is 10. The nominal radius of the ring is 10. Okay, and then fit it. Excellent. Exit and join it. Because this was a sketch, you cannot do the problem later. You cannot mesh it later without joining it. Okay, so it's already picked. It was orange. So you say sketch one. Say okay. Good. Apply material to it. Metal. Oh, apply material right there. Metal, steel on that part. We say okay, and the properties that I'm giving you in the homework is not exactly what's in the database here. So this is going to be 3, and the Poisson ratio is 0.3. So I changed it so that I'm consistent with what I'm asking you to do. If you said use the default properties of steel, that's fine. So just go ahead. Oops. Try it again. 0.3. I think there was a comma 3. Okay. Very good. Okay. Now, save it. File, save management, save as. On the desktop, I make a folder, a new folder, and I'll call it homework 2 lab 52. Okay, right there. Homework 2 lab 52. And I'm going to call this thing exactly the way you have to do it for submission of your homework or test. 1, 2, 3, 4, 5, 6, 7, 8, 9. Your student ID dash your last name Timoshenko. Then any identifier that helps you to find out what's going on. For example, homework 2, lab 52, problem 1. Maybe half a circle or something that you understand what problem 1 was later on if you ever had to look at it. So we say fine and say okay. Now we're going to go to generative structure analysis. There is no solid part here, so CATIA won't do any meshing for you. It's a static problem though. And so you have to do the meshing yourself. This is beam element right there. You see that? Not solid part, beam elements. That's what the most appropriate element is. Do not model this thing with solid element. That is not the most appropriate element. You select it, and if I had not joined this thing, I would not be able to do that. And I use the, let's use this, I don't know, element size point 3, something like that. You say okay. I think I keep typing comma 3. Point 3, say okay. And it's already meshed. If you want to see the mesh, right click mesh visualization and you zoom in. You're going to see your element number. Let's zoom in further. You're going to see your element number. This is element number 73 going between nodes 74 and 75 because I'm using linear elements. It has 2 nodes, and this is why there's only 2 nodes. Each element has 2 nodes. Okay, good. Now immediately file, save management, immediately save the analysis under this type of a thing. Let's remember what this thing was. So save as in the right folder. So I put down your student ID number 1, 2, 3, 4, 5, 6, 7, 8, 9. Timoshenko's student ID number, Timoshenko, that's the last name, dash. Now this was homework 2, lab 52, lab 52, dash problem, problem 2, problem 1. This was problem 1. Problem 1. Half a ring if it helps you to remember. Say okay and say okay. Now, deactivate your mesh, right click, deactivate your mesh. Now, this top point being in the plane of symmetry xz does not move in the direction y, okay? If a point of the beam lies in the xz plane of symmetry, it does not move in the direction y. XZ plane, no displacement in Y. Rotations, exactly the opposite. So if this is checked, corresponding rotation is free. If these are free, these translations are free, corresponding rotations are fixed. So this thing is actually the symmetry of, by the way, this applies also to the bottom. So why don't we do that? Why don't we take both of these, okay? And let's give it a name. So this is symmetry of the top and bottom. Symmetry, top and bottom. Okay, good. Bottom points, right? All right, good. Now, we want to push this thing down by some amount. So first, by the way, this top point, this diagram suggests that it is pinned. You can see that. So why don't we pin it? It already cannot move in the direction x and direction y because of the symmetry. But now we're going to say, okay, this top point does not, because it's a pin, does not move in the direction x and y. Okay, and I'll call this thing top pin. When I did it for the first group, I I forgot to fix the X. Okay, so it was the whole thing was moving out of the plane. So I had to come and fix that a couple of times until it worked. But here you're getting the benefit of that. So that top point, because it's a pin, does not move in X or Y. With the first group, I forgot to do it in the direction X. That's why this whole thing was moving as a rigid body. I had to go fix it later on. Okay, very good. This saves a little bit of time. Now, this point is going to be pushed down. In order for me to push it down, first I say, I push it by amount 0. So in the direction Z. So this point, any of these restraints which are bothering you, you can just hide it. See that? Right click, hide. Let me see now. Not this one. This is the top. Yeah. Right click, hide. See that? If it's blocking your view, just hide the stuff. Okay. So this point is going to be 0 displacement because I want to push it down. Okay, push it down. So enforce displacement on that thing. I want to push it down by the amount 0.01. That's exactly correct value because I did it for the area group. One thing I've forgotten to do is to specify the cross section of this, the cross section of that. So you go to 1D property, you select that, and it's a cylindrical beam. You go there, and it's the correct radius. Radius is 1. That's because I did it for the first group, lab 51, and it was, the values were already there. Now, this guy I hid. Okay, so remember I hid it so you can see it better. Now, when I get this thing to run, it will bomb out, and you'll see that. You'll see why. Okay. You can look at the deformation, and let's see if we can animate. We can see that it is like it's spinning about this axis. So let me make the scale bigger so that you can see it, perhaps maybe 10 times bigger. You see that? It is spinning about that axis. And there is a reason. Because when you go back to that problem, the drawing, and stare at it for a while, this pin does not prevent this from spinning about that. So what we have to do is say no rotation of that point about the z-axis. So you can see this right there. So we come here. Let me deactivate this plot. Deactivate it. Okay. So what is that? User defined on that point. No, not that point. Sorry, the top one. User defined on that top point. No rotation about the Z, which means take away that spinning motion. Maybe I should rename these things. So this was avoids prevent spinning. Prevent spinning. Okay. The other one was the pin condition. This one, what was this? I can't remember this. Oh, that was pushing it down to push down. I made it first. I made it 0. Remember, push down. I needed to make it 0 first. Okay. Now let's save this. Save the analysis and make another run and pray. Let's see what happens here. Let's look at the deformation. This thing is also spinning about this axis, right? There's two ways to fix this. One is to say, hey, you point, you cannot come out of the XY plane. That's one way of doing it. The other way is to say you cannot rotate about this direction. Okay, you cannot rotate about this direction. They both do the same thing. So let me deactivate this plot. There is no preference of one over the other. So for example, I say, yeah, here, don't come out of the plane. That is going in the direction X. Don't go in the direction X. Here. Don't move in X. Don't come out of the plane. Don't come out of plane. Okay. Say okay. Let's run it. Uh, That's okay. So let's not worry about that condition. Let's see if it worked first of all. So activate this, change the scale to default. You got some, oh wow, wait a minute. This point could not go in the direction, that pin, that pin should have stopped it from direction X, Y, Z. Yeah, I forgot to do that. Top pin, right there, X, Y, Z. Run it. Excellent. No messages, no warning messages. Let's look at uh, the 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 animation. See, before it was coming down here, not anymore. So let's see now. Deactivate this. Let me look at the displacements. Okay. Change the rendering here. Double click average ISO. Biggest displacement at the bottom. Look at the front view. It's easier to see what's going on. Okay. Right there, and you animate it. This thing comes straight down. It doesn't go to the left, doesn't go to the right because of symmetry. It comes down by the amount 0.01. Obviously, the top is pinned. Now, I just want to point out, those of you who do a little bit of thinking, you may look at this and say, wait a minute, what you have done after all these changes that you made, that top is actually clamped. And you're absolutely right. I did not say clamp here, but the effect of the load is that as if this was actually clamped up there, because it cannot go out in and out of the plane, it cannot spin, okay, and that really makes it a clamp up there. So could you have clamped the top and done the symmetry at the bottom and then push it down? Yes, but you're lucky if you don't know that that was a sheer coincidence. Then you were lucky. Okay. So you did something that maybe you didn't know the reason, but it happened to be correct. Now, what is the force that is needed to do this? So let's do it like that. Right click, uh, create a global sense, reaction sensor, resultant sensor, and then reaction sensor. And then you select the thing that you use to push it down right there. See that? You use this thing to push it down. First you made it 0 and then you changed it. And then update, you get almost 760 pounds. This is not the final answer. You have to multiply this thing by 2. This is the force needed to push this thing down half as half of the model down. To push the entire model down is double of that. And I think I forgot to mention that in the lab one that I recorded this. I didn't do that because uh, they were not supposed to submit this problem. They were supposed to do the second one. But anyway, they can watch this and see that. All right, save this. And now we're going to go and do the second problem. I don't need this guy. I don't need this guy. Now we're going to do the second problem. The second problem is right here. You don't have to submit this, but that's there. Now, there's two ways to do this problem. You can draw it as a sketch. Well, first of all, look at the structure here. The most appropriate element is beam. You don't model this thing as solid element, solid object, and then go mesh it. This end is clamped, left end is clamped, right end is clamped, and you take the middle point here and push it down by some amount. Okay, so when you think about it, this is actually you need to do half of the problem. Okay? So there's one plane of symmetry. XZ is a plane of symmetry. Okay, now there's two ways to do it. Draw this thing as a sketch and join it and proceed just like I did. Or you can draw this thing as a wireframe in space and make sure you join it. I'll talk about that in a minute. Okay, so let's go ahead and go that through. That's exactly what I did with the first recording. So let's start with the part. Immediately save it. File, save management, save as. I can put it in the same folder. Okay, so this is going to be, I'll call it problem 2. How about that? Problem 2. Everything else is correct. All right. So let's go and create 4 points in space, and the 4 points are a 0, 0, 0 right there. Another one is going to be 3 inches to the right, 3 inches to the right. Accidentally, I have created 2 points here, which I'm going to delete if necessary. then the 6 inches up, and then 3 inches to the right of this, which means 6 inches to the right of the XZ plane 6. And done. Cancel. I accidentally may have created duplicate node. No, I didn't. So 1, 2, 3, 4. Very good. So let's go ahead and create our lines. So one from here to there, another one from here to there, and the final one from here to here. Cancel. This is done. And I hide these points. These points are not needed anymore. And it's actually a good idea to hide it because you don't want accidentally to put a restraint on it or a load on it because CATIA doesn't know what they are. CATIA does not understand putting a force on a point, for example, versus a vertex. Let me hide these for a second and we'll talk about it more. Notice that when I select this end, it doesn't select that point because this is called a vertex, okay? Whereas it is point number 4, okay, which I hit. Look, right click, hide. If you select this point accidentally, may put the load or a clamp or whatever it is on that point, and CATIA will not understand what it is. It'll take it, but when you run it, it doesn't do what you were thinking of. Okay, very good. The other thing is I join these because if you don't join it, when you mesh it, uh, it'll mesh this, but there will be a node number on this side, which is going to be different. When you mesh this, it's going to have a different number. Okay? So if you don't join this at this point, at this location, you have multiple nodes, one from the top one from the vertical line, one from the horizontal line. Now you can avoid that if you're willing to go into the advanced meshing tool. I'm trying to avoid this. That being the case, I'm going to say join it. All these three, join them. Okay, and now there's no danger of what I just explained to you. Now let's apply material to it. Default material properties of steel. Metal, steel, okay. All right. Now we're going to save this before we go to the finite element module. So you go to generative structure analysis. There's nothing there to CATIA mesh. You have to do that yourself. Now, right there, because you join it, when you select this, everything is selected at once. If you had not joined it, not only you would have duplicate node, but also you could not do this thing at the same time. In fact, that's the reason you have to do it 3 times, 3 meshes, and this is why you get duplicate nodes on the side. But I joined it, it doesn't matter, so it's okay. All right, it did it. If it's not closing, don't worry about it. Just go ahead there and cancel that. Oh, try it again. Let's see now. There, say OK. It closed. The mesh is there. Right click mesh visualization. You say OK. You zoom in. You zoom in. You zoom in. From this side, the node number is 3. You can see that. From this side, the node number is also 3. If you had not joined, this would not have happened, and there would have been a gap there. And for that gap, you had to have used something that's called a connection, a rigid connection, which I'm not doing at this point. You will see that stuff later on in a different context. Okay, so analysis. Let's save it. File, say management. Okay, so I want to use that kind of a thing. Save as. Uh, oh, good. So all I have to do is to change this into problem 2. Okay. Student ID number, your last name, some description, and then you can upload the stuff into either for testing, for the test purposes or for homework purposes. This is good. Deactivate the mesh. Okay. This top point is clamped. That means all 6 degrees of freedom are fixed. I want to remind you that you could have done all 6 degrees of freedoms are 0 at that location. That would have been a clamp. That's what a clamp is actually. Okay. Now this point is on a plane of symmetry. The plane of symmetry is xz. So user defined restraint. Let's uncheck all of these. This point does not move because it's on the plane of symmetry. XZ does not move in the direction Y, and rotations are exactly opposite. In other words, when this is checked, rotation is free. When these are not checked, rotations are fixed. And this is what the plane of symmetry means. Okay, now, maybe I should rename these so that they reflect what they are. So this one is a clamp, right click, properties. I'll call this thing plane of symmetry, or symmetry, bottom point, plane of symmetry. Okay, that's good. Okay, now I want to push this thing down by some amount. First, I have to make it 0. So I'm going to select this point, and if anything is blocking your view, just hide it. Right click, hide it. See that? So this point, I want to push it down by the amount 0. So first, I make it 0, and then I can change it. You could have included this thing in the other restraint that you just made, except that when you debug it, you get confused, you don't know what happened. Anyway, so I made it separate. So this is right-click properties. I'll call it pushing down. How about that? Pushing down. All right, very good. Say okay. Now we change it. Enforce displacement right there. And I think I said push this thing down by 0.001. Say okay. And I haven't specified the cross section of this. So you go to 1D. Let me try to run it and show you what happens if you forget to specify the cross section. Okay, so let's try to run it. You see that you get some kind of message. You see it? It says acquisition of field model failed, could not find a property, etc. This is what, that's because I forgot to do this. You click on it, you select that because you joined it, everything is going to be selected. The radius for that particular problem was 0.125. This is so big because it's for problem 1. Okay, right there. You see that? This is the cross-sectional area for this, right there. And save it, run it, always pray. Excellent. Deflection, there we are. Look at the front view. There we are. Isn't that the way it's supposed to be? Yeah, you can animate it. Plane of symmetry means that guy cannot go to the left or to the right. It's just coming straight down. Deflection, amount of displacement, I specified by 0.001. So there is 0.001 at this end. Okay. Uh, I think it was 0.001, was it not? Yeah, 0.001 inch. Very good. You can change the rendering here. You can double click on the screen meaning on these arrows, okay? Or you can go to the plot corresponding to that thing that you did and say average ISO material shading, okay? And there, you cannot plot the stress. You know why? And let me say it again, because in beams, the location, the stress, von Mises stress depends on the location around the or in the cross section, middle section, top fiber, bottom fiber, neutral fiber, somewhere halfway in the middle. So CATIA will not do that for you. We'll say that, hey, listen, I can't do it because this I'm kind of weak in the beam element type thing. There are some other packages which have they plot the von Mises stress at specific location, which is already predefined, or you can declare it. But anyway, CATIA won't do that. It will plot for you the principal stress, but unfortunately, the only principal stress that it can plot it is the axial one, which is kind of totally useless. Okay. Again, the reason it won't do that because principal stress, if you want to find it, also it depends on the location around the cross on at the cross section. So deactivate this, no problem. How much force is needed to create that deformation? So you go to the sensor, right click, create a reaction sensor. See, resultant sensor, reaction sensor. Now select the restraint that is pushing down and update, and you get this. So you get 0.67, almost 0.7 pound. So how much force is needed to cause this deformation? You were supposed to write it here. Previous exam problem, use 0.69, 0.7 pound, and you lose 2 marks. I don't know, you lose, yeah, you're going to lose. If you do that, if you do that, you're going to lose out of this. You're going to lose 4 or 5 marks. Okay, because you have to multiply it by 2. This you showed us, you know how the process works. You didn't tell us that you're thinking. Okay, that's the difference. Well, it won't be complete loss of 5. At least if you write 0.69, we're going to give you 2 points. We deduct 3 or something like that. Okay. So, anyways, this is good. Okay. And by the way, if I had done for this thing, if I had selected the clamp, it would have given me also the same thing. For example, let's check it out. So sensor, uh, resultant sensor, reaction sensor, now select the clamp and say update, again 0.679, because the force here is opposite to the force over there, equal and opposite, action and reaction. Okay, folks, so this takes care of homework number 2. Good luck.